Okay, so I couldn't find any videos on the internet that did exactly what I kind of wanted to put across for the last lab. We may reuse this in the lecture course, so if you're here from the lecture course, welcome. Um, but I wanted to talk about the basics of capacitors just as they relate to the simple circuits that we're going to be using them in, and also to the basic physics of what's going on in a capacitor. So a capacitor in a DC circuit, like we're looking at here, is this is the circuit symbol for a capacitor. So two straight lines. Occasionally you see a few other variations on this circuit symbol, but that's about it. And if you connect it to a battery, well, imagine that we've just connected it. And so what we're going to have is current. So remember, our current is the flow direction that positive charges would go through our circuit. Current would flow this direction, right? From higher voltage towards lower voltage. But of course, a capacitor is literally just a conducting plate and then some insulator in between, and then another conducting plate. So in that sense, it's essentially an open circuit. So no charges can actually go across the capacitor. And you might say, okay, well, why does any current flow at all? Because we learned, like lecture 2 in this course, that unless you have a completed circuit, you're not going to get any flow of charge. Well, as with a lot of things, there are some exceptions to that rule. And when you have a capacitor in this sort of open circuit, because there's an insulator in between, what you actually get is, well, our current, so our direction of positive charges flowing, means that you're building up positive charges as the current flows on this set of plates. And we know from, again, early on in the course that, and I don't actually have blue ink pen here, so I'll use green. But what that does is if you have a big buildup of positive charge here, well, that's going to repel positive charges from the other plate. And remember that before we started charging this thing up, before we attached this battery to our capacitor, the capacitor is just two pieces of conductor. Neutral, equal numbers of positive and negative charges. So by flowing this current, we're going to accumulate positive charges here. In other words, we're going to be driving negative charges away. And the presence of those positive charges means that it's going to push positive charges away from this second plate. And that leaves behind an excess of negative charges, an equal number. Okay? So what that means is, well, because we're pushing positive charges away from the second plate, that means that the current in the circuit, at least for a short period of time, will continue to flow because we're pushing those positive charges away from the second plate, so they can continue on through the circuit and complete to the negative terminal. Okay. Now this doesn't last forever. As you know, if you want to take a single positive charge, say we're talking about a positive charge here. We know electrons are the things really moving around, but remember, we're using the conventional definition of current, so we're talking about positive charges. So here's one. And say that a little bit of time has passed, so we've already stuck a bunch of positive charge on this top plate. Well, that means we're going to need a lot of force to make this extra positive charge move against the repulsive forces that are usually felt between positive and positive charges. Okay? We need a lot of force. We need some energy from this battery to put this positive charge onto that plate. And if we think about another positive charge after that positive charge, well, then it's going to need even more force, because then we'll have, 5 charges if we add that previous one to the plate. Well, then we need even more force, and if we add another one, we need even more force, and eventually the amount of voltage difference across the battery is going to limit the amount of positive charge it can deposit onto the capacitor. Okay? In fact, if you look at the loop rule, what the loop rule tells you is that the voltage sort of added to the circuit by the battery has to be equal to the voltage subtracted or working against the battery from the capacitor, because you can see that if you think about this as like a little battery, so you've got a positive and negative charge there, that if you shove enough positive charges onto this end, which means that an equal number of negative charges are left over here after you push the positive charges away to complete this thing, then you're going to have a voltage of the capacitor that's trying to push current the other way, right? Counterclockwise through the circuit, whereas the battery is trying to push it the other way. So it's like two batteries opposing each other in a circuit. And if you're looking for sort of, what that looks like in terms of voltage and current in this simple capacitor battery circuit, if we put maybe first current in red, and we start at a particular value, and at first there's no charges rather on the capacitor, and so current is going to flow really well, okay, but it's only going to flow really well for a moment, and then you're going to have to spend energy to shove more and more charges on here, and then as you accumulate charge, there's going to be this opposing voltage on the capacitor that opposes the battery. So what you end up getting in terms of current is something that looks like this, an exponential decay, okay? And to be clear, on the x-axis here, we've got time. But the voltage across the capacitor, so I'll put that in green, so voltage sub C, so voltage across the capacitor, right? As you accumulate more charge, the voltage across the capacitor gets bigger and bigger and bigger because it's kind of like a battery. It's maintaining this difference in positive and negative charge between its terminals. And it's a little more complicated than that with a battery. Remember, it's dependent on the chemical reactions that's happening there, et cetera, et cetera. But in sort of the 5 mile in the air kind of view, it's very similar. And as we accumulate charge on the capacitor, it works against the battery that's charging it, and so we start with no charge on there, so right at the axis, but we quickly grow such that we have voltage on the capacitor that cancels the battery. So where this flattens out is the voltage across the battery. So I'll call it Vs. So this would be Vs. And you can see that the capacitor is never going to accumulate more charge than the battery can push onto it. And the loop rule tells us that the voltage added to the circuit can never be greater than or less than the voltage opposing it in the circuit. So whether this is resistors dropping it or whether it's capacitors storing the charge, essentially, you're never going to get more than that. So that's where it levels out and sort of asymptotically approaches that value. All right. Now, if we think about a capacitor in an AC circuit, and this is what applies to some of the stuff we're going to talk about in the lecture with radios, and also what we talk about in the last lab for my lab sections. So we've changed the picture only very little. We replaced our battery with an AC source. We got our capacitor in there, and let's look at what happens here. All right. Now, first, we're gonna eventually draw a graph here. So I'll get it on the page. And this is again is going to be time on the x-axis. But remember that the AC source, instead of supplying a constant voltage, it's going to be applying, as you can kind of see in its symbol, a varying voltage, and it's going to go into the positive, then it's going to cross the 0, and it's going to go negative, and then it's going to go back to 0 and go positive again. And so if we wanted to look at the, say, the voltage applied to the circuit, okay? Let's look at that first. We used green for voltage in the previous graph, so we'll use it here. So we'll see voltage from the source. Well, that's just going to look like a sine wave, right? So we start here, and we go up, and we go down, and we go up, etc., etc. All right? Not a particularly good sine wave. And got a little too curvy there at the end, but that's what we get from the source, right? That we know that from what we've looked at with AC generators and stuff like that, so we're all set there, okay? So during this part where the voltage is rising, okay, and it's continuing to increase, well, that means that current is going to be flowing this way. It's going to start small, and it's going to get bigger and bigger and bigger, but basically, you're doing a similar thing to what we did in the DC supply case, except that the amount of voltage applied is varying, so the size of this current flow is varying, but it's still going up and up and up and up and up. So the amount of charge being deposited on here, so the rate at which that charge is deposited changes, but we're still pushing positive charges onto this top plate, and that means that we are driving positive charges away from the bottom plate, and so the current can kind of complete the circuit, and all right, everybody's happy, okay? Things are looking familiar at this point. However, all right, once you start decreasing, right, you get up to a peak in voltage supplied by the AC source, and now we're starting to decrease. Well, that means that at some point the voltage on the capacitor is actually going to be greater than that on the AC source, and that means that it's going to try to drive current, and let me actually use red to represent current, but and when we start declining, at some point along this decline, the capacitor will have increased its voltage, right along with how much it's being charged, to the point where if this voltage from the AC source is dropping off, well, now we've got this nice big voltage source from the capacitor, so it's going to try to drive current back this way, right, away from its positive terminal, just like a battery, and towards its negative terminal, rather, okay? Okay, that's as it declines, as the voltage from the source declines, okay? So, in a sense, the capacitor is going to shift the amount of current that's flowing in the circuit, because if you just looked at the source voltage, you'd expect the current to be going up and up and up, and then going down and down and down, and then it's supposed to be reversing direction, and then it's getting smaller and smaller and smaller, and then it reverses direction again, it gets bigger and bigger and bigger. But because of this effect, because the capacitor, when the voltage from the source drops off, well, now there's nothing holding this charge on the capacitor will start acting like a little battery itself. It'll try to start driving current the other way, okay? And what that results in the circuit is a shift in the moment in time between when the source voltage is at a maximum and when the current flowing in the circuit is actually at a maximum, right? So if you were to connect the AC source and you were to wait until it sort of equilibrated and it was in sort of a steady state, what you would actually see is the following, which is kind of bananas. You get a peak in the current when the source voltage is 0, and that current drops there, so it's 0 when when the source voltage is at a peak, and then it comes down here and is a peak in the other direction, well, a trough in the other direction, Okay, and then again a 0 when this is at a trough, and then up here, and then back down here. And this is your current in circuit. Okay. This is weird. All right. Now, the effect here is much greater than what you saw in the series RC circuit, because the resistor has the effect of making the circuit act a little bit more normally. In other words, when you just have resistors in a circuit, then when the voltage is high from the source, then the current in the circuit is also high. Okay. So having a resistor in series here has the effect of sort of shifting the current back towards where the source voltage would otherwise say it would be. But when you just have a capacitor and no resistance in the circuit at all, what that's telling you is that the current, okay, in the circuit is at a maximum when the source voltage is at a minimum, minimum absolute value, so 0. And the current in the circuit is at a 0 when the source voltage is at either a peak or a trough. There's an equation that tells you what this must be. Okay? It tells you that the rate change in the voltage is related to the value of the current. Okay, so you can see that the rate change of the voltage, so the slope of the voltage curve, is at a maximum at this point, and so the current's at a maximum, positive. So positive slope, so positive current in one direction. And at this point, the slope of the voltage is at a minimum, or a 0, right? And so the current is at a 0. And so on and so forth, right? You've got a maximum negative voltage here, so we've got a maximum other direction of current, and et cetera, et cetera, et cetera. Okay? That's the effect of the capacitor. Essentially, because it gets charged by the current being driven by the AC source, but then allows the current to be maintained when the AC source's voltage is actually dropping off, you get this shift in the current actually flowing in the circuit at that particular moment versus the voltage applied to the circuit by the source at that moment. And the reason for that is that as you put charge on the capacitor, the voltage across the capacitor also rises. And if the voltage from the source ever drops below, so as it sort of comes down the curve, the voltage that the capacitor has, because of this difference, this separation of charge, right, this positive and negative across it, well, then the capacitor starts acting like the power source and trying to drive current the other way through the circuit. And so you get this shift in the current versus the source voltage in this simple power source and capacitor circuit. So I hope that was useful to you. Skip around. Maybe I repeated a few points too many times. We're up to about 18 minutes here, but thanks for viewing, and I hope this helps.